Welcome to this session. This session, we are going to derive the Simpson's third rule for numerical integration. First, recall that the general integration formula based on Newton forward interpolation formula is that if I have I integral from A to B, f of x dx can be written as integral from x naught to xn of f of x dx is the same as nh into f naught plus n over 2 fast forward of f naught plus n into 2n minus 3 over 12 second forward plus n into n minus 2 squared over 24 third forward of f naught plus other several terms. This is what we call star. Now, consider the function, or can say curve y f of x as drawn below. Now, let this be the y-axis. Let this be the x-axis. So this is y, 0. So let this be the arbitrary curve, y equals to f of x. So we're interested in integrating from A to B, and then so we divide this region into a number of sub-intervals. I'll just say that this is pattern continuous. So this is what we call the x naught, and this is what we call the xn. So this is x1, this is x2, this is x3, this is x4, this is x5, this is xn minus 1, xn minus 2. Now remember, the value of the function when this is x naught is f of x naught, which can be noted as f naught. The value of the function at this point here is f of x1, which can be written as f sub 1. So this is f1. The value of the function at this point is f of x2, which can be written as f sub 2. Here is f of x3 or f sub 3, f sub 4, f sub 5, etc. So this is f sub n. This height is f n minus 1. This is f n minus 2. Now, the interest, when you say that you want to integrate and find the value of the integral from A to B of f of x dx is the same as area under the curve y equals to f of x equals to A, and x equals to B. So simply that means we are interested in finding the area, what I'm shading, all this shaded area. So what I'm shading is what is equivalent to the integral that we are interested in evaluating. Now, unlike the case of trapezoidal rule, where we get area of one strip at a time, this time round now we get the area of two strips at a time. So we say putting n equals to 2 into that general integration formula, putting n equals to 2 in star, and taking the curve through 3 points, x0, f0, x1, f1, and x2, f2 as a parabola. So when we have 3 points, we can define a parabola of simply a polynomial of degree 2. So the third, fourth, etc. differences approaches 0 or are assumed to be 0. Hence, we have, now this is what I mean, that now we are taking the these points. We are taking this point is what is x0, f0. This is the point that is x1, f1. This is the point that is x2, f2. So it's like we are taking these two strips, this and this strip as a whole. And so when you have 3 points, we can define a polynomial of degree 2. So that's why we are saying that we are approximating the curve to be a polynomial, a parabola or a polynomial of degree 2. So we'll say I1 is given by the integral from x0 now to x2, because starting from this to this point here. So I'm moving from this point to this point here, of f of x dx is equals to nh, n is 2. So we'll have 2h into f0. And remember, the next term is n over 2. So when you put 2 over 2 is just 1. So we'll have forward of f0. And then plus, next term is n into 2n minus 3. So when you put here 2, we'll have over 12. 2 into 2 times 2 is 4 minus 3, and then over 12. 4 minus 3 is 1. 2 over 12, or 2 times 1 is 2, divided by 12 is 1 over 6. So we'll have 1 over 6, second forward of f0. So that's the formula. Because the third, fourth, etc. differences are assumed to be 0. So that now, from the general formula, this is what we have. And remember that forward of f0 is given by forward f1 minus f2, f0. And so when you say second forward of f0, we'll have forward of f0, f1 minus forward of f0, which is f2 minus f1 minus f1 plus f0. So remember, just using forward of Fk is Fk plus 1 minus Fk. And so if you were to define second forward of Fk, will be second forward, will be forward or first forward of Fk which is the same as writing forward. This by definition is Fk plus 1 minus Fk. So which will be forward of Fk plus 1 minus forward of Fk. And so forward of Fk plus 1 is Fk plus 2 minus Fk plus 1 minus forward of Fk is Fk plus 1 minus Fk. And so you see when you simplify, this will be Fk plus 2 minus Fk plus 1 minus Fk plus 1 minus minus is plus Fk. So that's why we have Fk plus 2 now minus 2 Fk plus 1 and then plus Fk. So this will give us F2 minus 2 F1 plus F0. So that now I simplify this part as I'll have 2h into F0 plus forward of F0 is F1 plus F0 minus F0 minus F0 and then plus 1/6 into this we have gotten to be F2 minus twice F1 plus F0. And then let's simplify that expression. So I'll have 2h into F0 plus F1 minus F0 plus 1/6 F0 minus, this will give me 2/6 F1 plus 1/6. Remember, this is F2 not F0. This is 2 F0. Now, this and this cancels out. And we have 2h into F1, collecting like terms. F1, let me start with 1/6 F0, and then F1 minus 2/6. So 1 minus 2/6. That is 2/3 F1 plus 1/6 F2. So this is I1. Then I'll have I2, this same I1. Now this one can be, if I factor out 1/6. Remember, if I want this one to be 6, if I have 2 over 3. If I want my denominator to be 6, I just simply multiply both sides by 2. So 2 by 2 is 4, 3 by 2 is 6. So this can be written as 2h into 1 over 6 f naught plus this 2 over 3 the same as 4 over 6 f1 plus 1 over 6 f naught f2. So then I factor out 1 over 6, so I'll have I1 is 1 over 6 times 2 is now a third into f naught plus 4 f1 plus f2. So that is I1. So I1 taking integral from x naught to x2. So it's like we have already done this up to this part, up to this point. So next step, we pick from now x2 to x4. So similarly, I2 would be the integral from x2 to x4, f of x dx, which is the same as 2h into, now remember when you say x2 to x4, the starting ordinate is f2. Now it's not f naught. So the formula here, you write this one as f2 not f naught. So I'll have f2 plus forward of f2 plus 1 over 6 second forward of f2. So we'll have 2h into f2 plus forward of f2 is f3 minus f2 plus 1 over 6 into, this will be f4 minus twice f3 plus f2. Please work out that one and see that that is multiplication, which will give us 2h into f2 plus f3 minus f2 plus 1 over 6 f4 minus 2 over 6 f3 plus 1 over 6 f2, which will be 2h. And then at this point, these two values cancels out, this and this. And so we'll have f3 minus 2 over 3. So we'll have 1 minus, so I can start with 1 over 6 f2. 1 minus 1 over 3 is 2/3. So plus 2 over 3 f3, and then plus 1 over 6 f4, which will be given by 2h. I can write this one as 1 over 6 f2. So if I want the denominator to be 6, then I multiply both numerator and denominator by 2. So I'll have 4 over 6 f3 plus 1 over 6 f4. And then I factor out a 6, which will give me h over 3 into f2 plus 4 f3 plus f4. So this is I2. So similarly, I3, you can work it out and find that I3, the integral now from x4 to x6 of f of x dx will be h over 3. If I2 is given by this one, so I3 should be giving us F4, F3, F3 plus 4, F4 plus F5. This is I2 is given by F2, F3, F4. So this will be F4, now F5, and then this should be 6. Because we are starting at F4. And then I4 will now be the integral from x6 to x8, f of x dx. And when you work out, you should get h over 3 into f6 plus 4 f7 plus f8. And this pattern continues up to now. You see that at every point, then in will be the integral from now. Integral from this, you see, this always, these subscripts are always even numbers. If you check from the start, this is 2, 4, this was 0, 2. So they are multiples of 2. So therefore, in will be given by x 2n minus 2 up to x 2n f of x dx. And this will be given by h over 3 into f 2n minus 2 plus 4 f of 2n minus 1 plus f of 2n. So that's the general formula for finding the area for 2 strips. So I is given by I1 plus I2 plus I3 up to plus In, which will be given by a head h over 3. The first one was given by f0 plus 4 f1 plus f2. I2 was h over 3 into f2 plus 4 f3 plus f4. I3 was h over 3 into f4 plus 4 f5 plus f6. I4 is h over 3 into f6 plus 4 f7 plus f8, all the way up to the ith one is h over 3 into f2n minus 2 plus 4 f2n minus 1 plus f2n. And because each of the terms has h over 3, then we factor it out. So I is equals to h over 3 into f0 plus 4 f1 plus f2. This other one will have f2 plus 4 f3 plus f4. And then plus this one we have f4 plus 4 f5 plus f6. This one we have f6 plus 4 f7 plus f8 plus other terms. This last one we have f2n minus 2 plus 4f2n minus 1 plus f2n. Now there's a pattern you can see that this will be 2, this will be 2, this will be 2. So also expect this one to have an f8 here, and also expect to have an f2n minus 2 here. And these odd numbers, they're always 4. So we can say I is equals to h over 3 into f naught plus 4 f1 plus 2 f2 plus 4 f3 plus 2 f4 plus 4 f5 plus 2 f6 plus 4 f7 plus 2 f8 plus, then you also expect to have this one to be twice f2n minus 2, and then plus 4 f2n minus 1, and then plus f2n. Now we can rewrite this I as h over 3 into the extreme ordinates. They are not affected by these multiples. So just write 2n. And then plus, you see we have 4, f1, f3, f4, f5, f7, all the way up to f2n minus 1, and then plus 2, all the way f2, f4, f6, f8, all the way up to f2n minus 2. So this is a formula. This is the Simpson's third rule. This is the Simpson's third rule, where the interval AB must always be divided into an even number of subintervals. Because if you remember, we are taking 2 at a time. So that's a very key thing to apply that rule. And we can simplify if we call this one, this formula alpha. So you say alpha can be simplified as saying the integral I from a to b of f of x dx, which is the integral from x naught to xn, f of x dx, is equals to h over 3 into x plus 4o plus 2e, where x means sum of end ordinates, o means sum of odd ordinates. And then E means sum of even ordinates. So that is the Simpson's third rule. Thank you.